From trigonometry, the area of a triangle is given by half the product of any two sides of the triangle by the sine of the angle in between. So if we take B and C as the two sides of this triangle, then the area is a half BC sine alpha. Now we will show that the area can also be calculated by taking half the magnitude of the cross product of vector AB with vector AC. We know from the definition of the cross product that the magnitude of the cross product is the magnitude of AB times the magnitude of AC times the sine of the angle in between the two vectors. Well, the magnitude of AB is just C, that's the length of this vector, and the magnitude of AC is B, so we have C times B, and alpha is the angle between the two sides or the two vectors. So, see, indeed we do get this. We just have to stick a half in front to get the area of the triangle. Now let's consider the moment of a force. The moment of a force is also known as the torque. So we are interested in the moment of this force F about the point O. So in a rough sense it means the turning effect of the force F about the point O. To get that turning effect we need this vector R. Now R is any vector whose tail is at O and whose head is a point on the line of action of F. So here's one possible R. Another possible R has its head at this point here. So we could use this vector for R. It turns out that the moment of F about O is given by R cross F. And R, the value of R cross F doesn't depend on where R is, as long as its head is along the line of action of F. To see why that's true, we use the definition of R cross F. Well, that's the magnitude of R times the magnitude of F times the sine of the angle between the two vectors. So if we move R so that its tail is here, then this is the angle between the two vectors. Put the tails together to get the angle between the two vectors. Now let's consider the magnitude of R multiplied by the sine of theta. Look at this right angle triangle here. So we drop a perpendicular from O to the line of action of F. If we multiply the hypotenuse, which is the magnitude of R, times the sine of theta, we will get the side opposite theta, which is OD. So we should have OD here, the distance from point O to D. So we see that in the definition of the magnitude of the moment of the force F about 0, we have this quantity, the distance of O to D. So it doesn't matter where R is, we're always going to get OD. So I mean I could have done the same for this vector here, and this angle would be theta, and we multiply the magnitude of R by the sine of theta, we will always get the distance of O to D. So you see that we can write the magnitude of the moment of F about O as the distance of the point O to D multiplied by the magnitude of F. So we multiply the shortest distance of the point O to the line of action of F by the magnitude of F. Let's look at this example here. Here we have our vector F. It acts at the point with coordinates 14, minus 3, 6, and we want to take the moment of force F about the point P. So we need a vector R. Now vector R can be any vector whose tail is at the point P and whose head is any point on the line of action of F. Now, obviously it's easier to use this point because we're given that this point is on the line of action of F. We could pick other points, but that's more work, we don't need to do that. So we can use this particular R. So how do we get this vector R? Well, we take the head of vector R, 14 minus 3, 6, and subtract the coordinates of the tail of vector R. So we subtract corresponding components. So the I component is 14 minus 2, which is 12. The J component is minus 3 minus minus 2. That's minus 3 plus 2, which is minus 1. And the K component is 6 minus 1, which is 5. So we have to get the cross product of R with F. And the easiest way to do that is to use this determinant method. So the first row involves the ijk basis vectors. The second row is the components of vector r. That's the first vector that appears in the cross product. And the third row is the components of the second vector, which is f. So that's 3, 4, 5. So, as we saw in the previous video, we need to calculate this determinant. So we take I and multiply it by the determinant of minus 1545. And we sign that positive sign. Then we go to the next entry in this row. We make it negative following the checkerboard pattern. So we minus j times the determinant of the matrix that's left when we cross out the row and column that j is on. So that's 12, 5, 3, 5. And finally we go to k. This has a positive sign in the checkerboard pattern, so we plus k, cross out the row and column that k is on, and take the determinant of the remaining 2 by 2 matrix. So to get the determinant of this matrix, we've minus 1 by 5 minus 5 by 4. So that's going to give us minus 5 minus 20. It's minus 25. Here we have 12 5s are 60 minus 15. That's plus 45 times this minus sign gives us minus 45. Over here we have 48 minus 3. 48 plus 3 is plus 51. So if r is in meters and f is in newtons, then the units of the moment vector is Newton meters. Now if you want to see the direction of the moment vector, we have to move r so that its tail is at the tail of f. So I'm just copying out this diagram. We want r cross f. So we would have to rotate r towards f. So that's an anti-clockwise rotation. So that means that r cross f is a vector that's coming out of the screen. So we think of an arrowhead. Okay, so we have an arrow and its tail. And if we're looking at the tip of the arrow, we just see this dot, a circle if you like, with a dot at the center. So the r cross f is an arrow pointing out of the screen, so we see the dot. If it's pointing in the screen, we would see the tail, which we could represent symbolically like this here, a circle with a cross on it, if we're looking at the other end of the arrow. That's not what's happening here. We're looking at the tip of the arrow. R cross f is coming out of the screen. What about its magnitude? Well, we can just square the components, sum them, and take the square root if we want the magnitude of the moment. As a reminder, I use these words interchangeably. They have the same meaning, moment or torque of the force.